Alright, this is number 69 in chapter 7. I didn't draw the diagram just because it's in the paper. But for this problem, you're going to want to find the velocity for part A. You're going to be using the conservation of energy. So, looking at this, point A is the equilibrium. So you're going to use this equation. So the kinetic energy at A plus the potential energy at A plus the added work, which is you pulling the spring back, is equal to the kinetic energy in part B plus the potential energy in part B. So for this one, we need to find out what W is, because the kinetic energy at A and the potential energy at A is 0 because it's at equilibrium. So now it's just W equals KB plus UB. And we know that work is equal to force times distance, or delta X. So we can find out the force, the work by what we're given. So the force of the pull, which is the 20 newtons, times the change in the distance, which was a 0.25 between point A and point B. So W equals 20 newtons times the change in distance, which is 0.25 meters. So the work done is 5 joules. And then we know the equations for KB and UB. Kinetic energy is 1/2 mass times volume squared, and U is 1/2 kx squared. And the K is the spring constant. So we can plug this back in to solve for it. Or actually, let's just solve for these K's and B's right now. So we're not going to solve for the K because we actually need the velocity out there. So we're going to solve for U. So UB right here is equal to 1/2 times the spring constant times the distance squared, and that will give you 1.25 joules. And then you just plug that back into this equation. So we got 5 joules is equal to 1/2 mv squared plus the 1.25 joules. And you're just going to rearrange this so that you get velocity, which will give you, after you subtract this over, multiply it by 2, divide by the mass, and square root it, you get square root 3.75 joules divided by 0.5 kilograms, and that will give you a velocity of 3.87 meters per second. And then for part B, it says, when the back of the block reaches point B, you let go of the block in the subsequent motion. How close does the block get to the wall where the left end of the spring is attached? So it's going to be similar to this last problem. I'm just going to erase this really quick. Alright, so part B. Now you're just going to be looking at the same idea, KB plus UB plus W equals KC plus KB or UC. So this is point B, this is C, which is the end that you're looking for. With this, you're not going to have an added force and a kinetic at the end because you're looking for the distance. How close does it get to the wall? So your velocity is 0 in this case. That's why this goes to 0. So you plug in what we have, which we solved in the last problem for KB and UB, which was 3.75 joules plus 1.25 joules is equal to 1/2 kx squared. You just rearrange this around and you get square root of 2 times 5 over 40, which is x, which equals 0.50 meters. And you gotta take into account the overall distance that you traveled from equilibrium to this point. So it would be 0.60 minus 0.50 equals 0.1 or 0.10 meters is the distance.